Even our most advanced machines could not perfectly rebuild it. The Great Pyramid of Giza is a monument that challenges everything we think we know about the ancient world. This is not a story of myths or visitors from the stars, but of real human genius, a sophisticated engineering system that has been misplaced by time. By the end of this journey, you will see this ancient wonder not as a magical mystery, but as a solvable puzzle of brilliant logistics and physics. How did a civilization with no wheels or iron achieve such impossible precision? And why was their remarkable blueprint seemingly erased from history? What does it truly mean to say that a technology has been lost, that precision is not a lucky accident? It is the signature of a deliberate and sophisticated method. Think about the sheer physical reality of moving a single one of those blocks. Each one weighs as much as 2 modern family cars. Now, picture not one, but 2.3 million of them. The total volume of stone used could build a wall 3 feet high and 1 foot thick that would wrap entirely around the entire coast of France. This is a logistical challenge that would strain even our modern construction industry with its cranes, trucks, and computer-aided planning. Yet, the builders of the Great Pyramid managed it without any of those tools. Their workforce, while large, was not the endless sea of slaves often depicted in old stories. Archaeological evidence points to a rotating, skilled labor force who were housed, fed, and respected. This shifts the mystery from one of brute force to one of brilliant organization. How do you coordinate thousands of people to cut, transport, and place millions of multi-ton blocks with near-perfect alignment over a 20-year period? The answer cannot be ropes and ramps alone. There had to be a system, a repeatable, teachable process that turned an impossible dream into a This is the lost engineering method we are searching for, not a single magical tool, but an entire operational blueprint for achieving the impossible. That operational blueprint leaves its first fingerprints in the quarries, far from the final glory of the pyramid itself. To understand the method, we must look at the very beginning of the supply chain, where raw stone became a precision component. The finest white limestone came from the quarries across the Nile, while the immense granite for the inner chambers was sourced from Aswan, over 500 miles to the south. These were not haphazard digging sites. They were the first stage of a grand, state-managed production line. A remarkable discovery, the diary of an overseer named Muon, gives us a window into this world. Muon and his crew of about 40 men were specialists in transporting the limestone blocks by boat. His records note deliveries, rations, and even the name of the reigning pharaoh, placing us directly in the timeline of construction. This single document shatters the old image of a mindless, suffering workforce. It reveals a rotating system of skilled laborers, organized into disciplined crews, who were housed in planned barracks near the Giza plateau and received regular wages in the form of bread and beer. They were not slaves, they were state employees executing a national project. The quarrying technique itself speaks volumes about their engineering mindset. Workers would carefully cut a series of narrow slots into the solid bedrock. Into these slots, they would drive dry wooden wedges. Then, they would pour water over the wood. As the wedges absorbed the water, they expanded with tremendous, controlled force, cleanly splitting the stone along a predetermined line. This is not brute force. This is applied physics. It shows a deep, practical understanding of material properties, how stone reacts to stress, how wood expands, and how to harness natural forces to do precise work. This principle of controlled, intelligent force over uncontrolled manpower is the foundational clue. The lost method was already in full swing before a single block ever touched the desert sand. Murray's diary gives us the destination, but the journey itself is the second great clue. How do you move a 2.5-ton block of limestone from a quarry across the Nile, or a 70-ton granite monolith from 500 miles upriver, and deliver it flawlessly to the construction site? The sheer physics of it seems to defy the era. The old Hollywood image of endless lines of people straining against ropes, whips cracking, is not just inaccurate, it's an insult to the ingenuity at play. Modern archaeology reveals a transportation network of stunning sophistication, a civil engineering project that rivaled the pyramid itself. The key was turning the landscape into a tool. Researchers now believe the builders created a series of purpose-built canals, branching off the Nile and extending right to the edge of the Giza plateau. Imagine a harbor complex bustling with activity, not with slaves, but with skilled boatmen like Murray and his crew, guiding barges laden with stone directly to the project's doorstep. This transformed the Nile from a barrier into a liquid highway, allowing the heaviest materials to travel with an efficiency that land travel could never match. But what about the final leg, from the harbor to the rising pyramid? Here, the method reveals another elegant application of simple physics. Experiments have shown that pulling a massive stone on a wooden sled across dry desert sand requires an enormous, almost impossible amount of force. But wet the sand just right, and everything changes. The water creates a capillary bridge between the sand grains, dramatically reducing friction. A small team could then pull a load that would otherwise require hundreds. This was about muscle, it was about lubrication. It meant preparing pathways, managing water resources, and understanding material science on an intuitive, practical level. This entire logistical network, the canals, the harbor, the prepared ramps and wet sled roads just support. It was the circulatory system of the project, a critical, repeatable component of the construction method. It shows us that the pyramid's builders thought like systems engineers, solving one impossible problem by intelligently redesigning the world around them. The transportation network solved one monumental challenge, only to present the next. With millions of stones now arriving at the base of the construction site, the builders faced their most famous puzzle, the act of vertical ascent. This is the third great clue, the ramp controversy. For generations, the default image has been a single, massive straight ramp extending from the desert floor to the pyramid's peak. It seems logical, but the math quickly unravels this idea. To reach the top at a gentle, workable slope, such a ramp would have been over a mile long and required more material than the pyramid itself. Its construction would have been a project rivaling the Great Monument, only to be torn down afterward, a staggering waste of effort that feels out of step with the efficiency we have seen so far. This forces us to reconsider. The ramp, if it existed, was not a brute force solution. It was likely a temporary, evolving piece of infrastructure, as cleverly designed as anything else. One modern theory suggests an internal spiral ramp, a corkscrew tunnel built within the growing structure's outer shell. This solves the material problem, but introduces others. How would workers navigate tight corners with 70-ton granite blocks? How would they maintain the critical external alignment of the pyramid's faces from inside a dark, enclosed ramp? Another compelling idea is a zigzagging ramp that climbed a single face, switching back at each corner. This would be a compromise, using far less material than a straight ramp while avoiding the internal stresses of a spiral. Each of these theories, while imperfect, reveals a crucial piece of the puzzle. They point toward a system that was adaptable, that changed as the pyramid rose. The ramp was not a static monument. It was a dynamic tool, built, modified, and ultimately dismantled as part of the grand operational plan. This temporary evolving scaffold is a key component of the lost method. It shows us that the builders thought in 4 dimensions, planning not just the final form, but every step of the journey to get there. This final act of lifting and placing the stones reveals the 4th, and perhaps most elegant, clue to their method. We have moved millions of blocks across the desert and up a temporary scaffold, but the last few feet of vertical ascent demand something different. This is where the ancient engineers demonstrated their true mastery of physics, moving beyond simple ramps into the realm of mechanical advantage. They possessed a tool that was ubiquitous in their world, a device so common it was used for drawing water from the Nile for irrigation. It was called a shadoof. At its heart, it is a simple lever, a long wooden beam balanced on a pivot, with a bucket on one end and a counterweight on the other. A farmer could lift a heavy bucket of water with minimal effort by using the weight on the opposite end. Now, scale that principle up to a monumental level. Picture a massive, pivoting wooden arm erected on the pyramid's rising tier. On one end, a cradle holds a 2-ton limestone block. On the other, a large container. Instead of pulling the block upward with raw manpower, workers would gradually fill this container with sand or smaller stones. As the counterweight grew heavier, it would gracefully lift the massive block on the opposite end, inch by controlled inch. This transforms an act of sheer force into one of precise, manageable calibration. It is a brilliant application of a simple concept, turning a tool for survival into a tool for immortality. Such a system could work in beautiful tandem with the ramps. A block might be dragged up a ramp to a certain height, then transferred to a counterweight lever for the final, delicate positioning into its exact, tight-fitting place. This is the signature of the lost engineering method. It was not a single secret, but a symphony of solutions. They understood the land as a tool with their canals, the materials as a tool with their wedges, and the very laws of physics as a tool with their levers. Each piece solved a discrete problem, but together they formed a repeatable, teachable process for achieving the impossible. The final ascent of each stone was only half the battle. Placing it was an act of precision that borders on artistry. This brings us to the 5th clue, the art of the perfect fit. Look closely at the Great Pyramid's remaining core blocks. They are massive, rugged, and seemingly haphazard, yet the joints between them are tight, often with gaps of less than a millimeter. This is not the work of chance. It is the result of a deliberate, on-site finishing process that turned rough-cut stone into a seamless puzzle. The real marvel, however, was the outer shell. For thousands of years, the pyramid was clad in brilliant white limestone, polished to a mirror-like finish. These casing stones were fitted together with such impossible accuracy that the gaps between them were said to be thinner than a human hair. A knife blade could not slip into the joint. This level of perfection could not have been achieved in the quarry. The blocks had to be placed, then perfected right where they sat. Imagine the scene on the rising tiers. After a massive block was levered into its approximate position, teams of workers would surround it with simple, effective tools. They likely used pounders made of even harder stone, like dolerite, to methodically grind the surfaces together. This was a slow, patient process of abrasion. One block would be rubbed against its neighbor, back and forth, with a slurry of sand and water acting as a natural polishing agent. Over time, the high spots would wear down, the angles would become true, and the two faces would merge into a single, continuous plane. This is a profound shift in how we view the construction. It was not a linear process of build then finish. Construction and finishing were integrated, two phases of a single, refined operation. Think of it as ancient additive manufacturing. Each block was a rough component placed into the growing structure, and then the structure itself was used as the tool to perfect that component. The pyramid, in a very real sense, built itself. This on-site calibration solved a critical engineering problem. It compensated for any tiny imperfections from quarrying or transport. It meant the builders did not need to achieve impossible perfection at the source. They only needed to get close. The final, flawless alignment was achieved through this patient, grinding collaboration between human skill and the weight of the stones themselves. The result was a monument that was not just stacked, but fused together, a geometric form so precise it has captivated the world for. That seamless fusion of stone, achieved through patient grinding, points toward a deeper principle at the heart of their method. It was an intimate dialogue with the natural world, a willingness to let the environment itself become the most powerful machine. This leads us to one of the most radical and elegant theories about their lifting technique, a hypothesis that flows directly from their known mastery. What if the final secret was not levers or ramps, but water? We have already seen how they used wet sand to reduce friction for transport. But a more profound idea suggests water was not just a lubricant, but the primary lifting mechanism for the pyramid's upper reaches. This theory proposes the construction of a sealed, water-filled shaft that spiraled up the growing structure's core. Imagine a massive, watertight wooden chamber or caisson built right into the pyramid's interior. A giant stone block, encased in its own floating container, would be guided into this shaft. Here, the ancient principle of buoyancy takes over. A floating object displaces its own weight in water. So to lift a 2-ton block, you only need to displace 2 tons of water. By carefully controlling the water level within the sealed shaft, perhaps using a simple lock system or a series of pumps, the builders could raise the block with astonishingly little effort. The water itself does the heavy lifting. Once the block reached the desired height, it could be floated out of the central shaft, guided into its approximate position in a waiting chamber filled with water, and then the water would be slowly drained away. Lowering the block with gentle, perfect control onto its bed. The evidence for such a system is, admittedly, speculative. No definitive remains of a giant internal water shaft have been found. Yet the idea is compelling not because it is proven, but because it fits the pattern of genius we have been tracing. The ancient Egyptians were master hydrologists. Their entire civilization was built on predicting and harnessing the Nile's annual flood. They constructed elaborate canals, basins, and locks for irrigation. The concept of using water's power for lifting was already in their toolkit with the simple shadoof. Scaling that principle up to a monumental level is a breathtaking, but logical, leap. It represents the ultimate expression of their engineering philosophy, turning the most abundant resource in their world into the primary engine for their greatest creation. Whether this specific water lift system was used or not, the theory serves a vital purpose. It pushes us to think as they thought, to see solutions not in complex machinery they did not have, but in the fundamental forces of nature they understood intimately. It challenges us to look past the stone and see the fluid intelligence that might have made it rise. This dialogue with the natural world extended far beyond the outer shell and into the very heart of the monument. The Great Pyramid is not a solid heap of rock. It is a carefully designed architectural machine, containing a precise network of chambers, passageways, and ingenious stress-relieving structures. This internal architecture is the ultimate physical blueprint of their method, a three-dimensional plan frozen in stone. The most stunning example is the Grand Gallery. This soaring, narrow corridor is an engineering marvel in itself, with its walls built in 7 overlapping layers, each one stepping inward. This corbelled design perfectly distributes the immense weight of the millions of tons of stone above it, preventing the ceiling from collapsing. But the gallery's true purpose remains one of the pyramid's great enigmas. Along its length are 27 pairs of mysterious, rectangular slots cut into the walls, and a central walkway flanked by stone benches. This was clearly not just a hallway. Some researchers suggest it functioned as a grand counterweight chamber. Imagine a massive sand-filled container suspended within the gallery's tall space. As it was lowered down the steep incline, its tremendous weight could have been used to haul the gigantic granite beams for the king's chamber up the ascending passageway. A simple yet monumental application of pulley-like mechanics. Others proposed the slots held a complex lifting device that ratcheted blocks upward, using the gallery itself as a stable track. Whether it was for lifting or balancing, the Grand Gallery's design reveals a critical truth. The builders were thinking in multiple dimensions from the very first foundation stone. They had to plan not only the pyramid's final external shape, but also this intricate internal labyrinth, ensuring its chambers and passages would remain intact and perfectly aligned as the mountain of stone grew around them. This required a profound grasp of projective geometry, the ability to visualize and plot complex interior spaces within a massive, unfinished structure. They were essentially drawing in 3 dimensions with multi-ton blocks, and their blueprint was executed with flawless precision. The internal architecture proves their method was holistic. It was a single, unified plan where logistics, physics, and geometry worked in concert, turning a pile of stone into a timeless geometric equation. This flawless internal geometry was matched by an equally precise relationship with the sky above. The Great Pyramid's 4 faces are aligned to the 4 cardinal directions, with an error of less than 1/15 of a single degree. To put that in perspective, if you laid a giant ruler along its base, the deviation from true north would be less than the width of a tennis ball over its entire length. This is not a lucky guess. This is celestial engineering of the highest order. How did a civilization without magnetic compasses or digital theodolites achieve such impossible accuracy? The old explanation of using simple shadow sticks at noon falls apart under scrutiny, as the sun's shadow is too fuzzy and moves too slowly to provide such a razor-sharp line. A far more compelling theory emerges from the night sky. Around the year 2500 BC, the North Celestial Pole was not marked by our familiar Polaris. Instead, it lay close to a star in the constellation of Draco, known to us as. For the ancient Egyptians, this star that never set was a fixed point of cosmic significance. Imagine an architect or priest astronomer standing on the leveled Giza plateau long before the first stone was set. Their tool was not a complex instrument, but a deep, patient observation of the heavens. They would have constructed a simple viewing enclosure, a long, narrow corridor, or a pair of permanent markers. Night after night, for an entire year, they would record the precise points on the horizon where rose and where it set. The exact midpoint between these 2 extreme points would indicate true geographic north with astonishing precision. This method transforms the construction site into a vast astronomical observatory. It required not just knowledge, but a cultural mindset that saw no separation between the earthly and the celestial. The pyramid was not merely oriented toward north. It was anchored to the very axis of the sky, a terrestrial echo of a cosmic order. This celestial surveying was the first, most critical act of the entire project, the foundational line from which every other measurement and angle would flow. It tells us the builders were not just masons, they were cosmic cartographers, and their lost method began not with a quarry, but with the silent, patient tracking of a star's eternal path. That celestial alignment was only possible because the stones themselves could be trusted. The ancient Egyptians did not just move mountains of rock, they understood them. Their mastery over materials was not magic, it was a deep, empirical science, refined through generations of hands-on experience. They knew the land like a painter knows their palette. The coarse, abundant limestone from the local Giza plateau formed the massive core blocks, providing a stable, economical heart for the structure. For the brilliant outer skin, they traveled across the Nile to the quarries, selecting a specific layer of fine, white limestone that could take a high polish and gleam under the desert sun. And for the most sacred, enduring elements, the king's sarcophagus and the walls of the burial chamber, they undertook a monumental journey to Aswan, 500 miles upriver, to quarry red granite. A stone so hard it can blunt modern steel tools, this was not random selection, it was a precise specification. They understood that each material had unique properties, and they developed specialized techniques to work each one. Shaping that Aswan granite is a staggering feat. They used pounders made of even harder dolerite stone, along with abrasive sand, to slowly, patiently grind the granite into smooth planes and perfect right angles. The sarcophagus in the king's chamber is so precisely squared that its interior corners are sharp and true, a testament to a level of craftsmanship that seems to defy the tools of the age. This knowledge was not written in formal textbooks. It lived in the hands and minds of guilds of master stonemasons, passed from experienced artisans to apprentices over centuries. It was a living library of applied physics and geology, where knowing how a stone would fracture, how it responded to water, or how it could be polished was critical, guarded knowledge. So when we speak of a lost engineering method, we are not necessarily describing a single catastrophic event that erased all records. The disappearance was likely far more gradual and human. The knowledge was tied to the project itself, to the sustained, state-sponsored demand for building on a colossal scale. When the age of the giant pyramids passed, the urgent need for that specific, large-scale logistical and material science faded. The specialized guilds, those elite communities of practice, would have slowly dissolved. Their hard-won secrets, no longer in daily use for monumental projects, became specialized lore, then forgotten techniques, and finally mysteries. The method was not stolen, it simply atrophied, like a muscle no longer exercised. The stones remain, but the intimate conversation between the builder and the material fell silent, leaving us to wonder at the fingerprints of a science we can only partially reconstruct. That intimate material science was guided by a higher order of knowledge, a language of perfect form written in stone. The Great Pyramid's geometry is not just a shape, it is a mathematical statement. While scholars debate whether its builders intentionally encoded constants like pi or the golden ratio, the sheer, unwavering consistency of its proportions speaks to a profound and standardized system of measurement. This was not guesswork, it was applied mathematics on a monumental scale. The ancient Egyptians possessed a unit of measurement called the royal cubit, roughly the length from a man's elbow to the tip of his middle finger. But this was not a vague approximation. Standardized cubit rods, some made of stone, have been found, ensuring every architect and foreman was working from the same exact blueprint. With this consistent unit, they could translate an abstract vision into a physical reality that could be communicated to thousands of workers across decades. The true genius of their system, however, lay in a specific geometric concept called the imagine you are an ancient architect. You need to tell a quarry crew, miles away, how to shape a block so that when millions of them are stacked, They create a smooth, uniform slope rising at a precise 51-degree angle. You cannot simply shout an angle measurement. They have no tools to measure. The solution was it was a practical, buildable ratio. It defined a pyramid slope as a relationship between horizontal and vertical distance. For the Great Pyramid, there was 5.5 palms of horizontal run for every 1 cubit of vertical rise. This meant a foreman could take his measuring cord and peg out this exact ratio directly onto a stone block or onto the growing face of the pyramid itself. It was a recipe, a repeatable instruction that could be followed by anyone with the proper training, ensuring every single course of stone maintained that iconic, unwavering angle from base to peak. This mathematical rigor transformed an overwhelming artistic vision into a series of simple, executable steps. Using nothing more than sighting rods, plumb bobs, and knotted cords, they turned the chaotic desert into a giant geometric construction site. The pyramid did not emerge from the sand. It was calculated into existence, its perfect form arising from the disciplined application of a beautiful and practical mathematical rule. The precision of their geometry reveals a deeper truth about the pyramid's construction. It was not just a feat of engineering, but a triumph of human organization. The true lost method may have been managerial as much as technical. This was the world's first true megaproject, a logistical undertaking that would challenge any modern corporation. Think about what was required beyond the stones themselves. You had to coordinate thousands of skilled workers, not as a single mob, but as specialized teams of boatmen, masons, carpenters, and surveyors. Each group needed clear instructions, a place to sleep, and enough food and water to sustain them for their rotating shifts, which could last for months at a time. This was a 20-year marathon, not a sprint, and it required a supply chain of breathtaking complexity. Every day, the state had to deliver thousands of loaves of bread, vats of beer, and portions of fish and vegetables to the plateau. They needed a constant flow of tools, copper chisels that wore down quickly, ropes made of papyrus, wooden sleds and levers, and tons of abrasive sand for polishing. All of this had to be scheduled, tracked, and distributed without a single computer or spreadsheet. The organizational chart for this project must have been a wonder in itself. At the top was the pharaoh's vizier, the ultimate project manager. Beneath him were layers of administrators, scribes, and overseers, each responsible for a specific domain, like the quarry operations Muir documented or the crew housing at the workers' village. These officials did not just give orders, they kept meticulous records on papyrus, tracking deliveries, work hours, and even absenteeism. This was not a society built on coercion alone. The discovery of workers' tombs near the pyramids, marked with honorific titles like Friend of Khufu or Overseer of the Craftsmen, tells a powerful story. These were not anonymous laborers cast aside. They were respected members of a national endeavor, given proper burials for their service. This suggests a hierarchical but motivated society where skilled work brought status and honor. The pyramid, therefore, was as much a social innovation as a technical one. It was a living experiment in how to coordinate human activity on a previously unimaginable scale. It created a blueprint for organizing labor, for turning the disparate efforts of thousands of individuals into the single, focused will of a civilization. That social machinery, the ability to plan, feed, house, and motivate a vast workforce for generations, may have been the most revolutionary invention of all. And perhaps the piece of the method that is hardest for us to truly recover. The true test of any theory is not in the blueprint, but in the doing. To understand how the Great Pyramid could have been built, we must step out of the library and into the quarry. This is the world of experimental archaeology, where scholars and craftspeople put down their books and pick up ancient tools to see if the proposed methods actually work. It is a process of learning by doing, a physical conversation with the past. One of the most famous modern experiments was led by a Japanese research team in the 1990s. Their goal was not to build a whole pyramid, but to test the individual steps of the process using only technology available to the ancient Egyptians. They successfully, a multi-ton block of limestone, using nothing but copper chisels and wooden wedges. They transported it on a reconstructed wooden sled over wet sand, confirming that a small crew could move an immense weight with surprising ease. And then, using a simple earthen ramp and sheer manpower, they raised the block into position. While their project was small in scale, its implications were monumental. It proved beyond any reasonable doubt that the fundamental components of the lost method were physically viable. The stones could be cut, they could be moved, and they could be lifted, all without magic or alien intervention. These experiments do more than just prove possibility, they reveal the human rhythm of the work. They show how the clever use of a lever, or a lubricated path, turns an impossible lift into a series of manageable, rhythmic pulls. They highlight the critical role of teamwork and coordinated chance, turning individual effort into a unified, mechanical force. Each successful experiment is a powerful rebuttal to the idea of impossibility. It chips away at the myth to reveal the method underneath, showing that the pyramid was not a single miracle, but a symphony of thousands of simple, well-executed techniques, performed with patience and precision over generations. This cumulative view of knowledge presents a powerful counter-narrative to the idea of a single, vanished blueprint. Some leading Egyptologists suggest we are not looking for a lost method at all, but rather tracing the clear, evolutionary path of a craft honed through generations. The perfection of Giza did not appear from a void. It was the final, breathtaking chapter in a century-long story of architectural ambition, one marked as much by spectacular failures as by brilliant successes. To see this, we must look south, to the earlier pyramids at Saqqara and the very first attempt, the Step Pyramid of Pharaoh, begun around 2630 BC, was revolutionary but fundamentally cautious. It was not a true pyramid, but a stack of 6 mastaba tombs, each smaller than the last, creating a towering staircase to the heavens. Its builders were mastering the art of building upward on a grand scale, but the smooth, sloping face was still beyond their technical reach. Decades later, Pharaoh, the father of Khufu who built the Great Pyramid, embarked on his own monumental journey. His first pyramid appears to have collapsed, a stark lesson in structural integrity. Undeterred, he moved to and began the bent pyramid. This structure tells a story in stone. Its lower half rises at a steep, ambitious angle, but then, visibly, the angle changes, softening for the upper sections. The most compelling theory is that the builders, seeing alarming cracks form in the inner chambers, made a mid-construction correction to prevent a total collapse. It was a brilliant, on-the-fly engineering save. Next and final project, the Red Pyramid just north of the bend, finally achieved the classic smooth-sided form. It is considered the first true, successful pyramid. This sequence, the stepped experiment, the catastrophic failure, the bent correction, and the final success, is not a history of lost secrets. It is a public stone and mortar textbook of trial and error. Each project taught the next generation of architects and engineers critical lessons about load distribution, internal chamber design, and the precise mathematics of slope stability. By the time Khufu ascended the throne, the state possessed not a secret scroll, but a living tradition of master builders who had personally solved these problems. The Great Pyramid, then, is not an anomaly. It is the culmination, the flawless execution of a century's worth of accumulated, hard-won knowledge. So why did this knowledge seem to vanish? The answer lies not in conspiracy, but in simple historical change. After the Fourth Dynasty, the sheer economic and social cost of such megaprojects became unsustainable. The Egyptian state shifted its focus and resources. The age of the colossal pyramid passed. The specialized guilds, no longer commissioned for such grand endeavors, gradually disbanded. The knowledge did not disappear in a single night. It simply ceased to be practiced at that scale, fading from active engineering into legend, waiting for us to piece it back together through the stones themselves. The plateau itself was the first and most critical component of the entire project. Every decision the ancient engineers made, from quarrying to placement, was rooted in a profound understanding of their immediate environment. This was not a blank canvas, but a carefully chosen geological stage. The Giza Plateau is a massive outcrop of limestone, a stone formed from the compressed shells of ancient sea creatures. To the builders, this was not just rock, it was a gift. It provided an immensely stable, level foundation, a natural plinth upon which to erect a mountain. They did not have to dig deep piles or reinforce unstable sand. They simply leveled the existing bedrock, creating a platform that has remained steadfast for over 4,500 years. This choice reveals a fundamental principle of their method: work with the land, not against it. But the plateau offered more than just a solid floor. It was also a literal quarry. The lower courses of the Great Pyramid, its massive heart, are built from this very same local limestone. Imagine the efficiency. Instead of dragging every single block from miles away, the builders could source millions of tons of material directly from the footprint of the monument itself. As they cut the foundation trenches and leveled the site, they were simultaneously harvesting the core building blocks. This turned a necessary preparation step into the first phase of material supply, a brilliant piece of logistical integration. Yet, they also knew the limitations of their local stone. While perfect for the hidden core, it was too coarse to take the fine polish they desired for the exterior. So they looked across the river to the quarries for their brilliant casing stones, and south to Aswan for the granite of the inner sanctum. This was not random importation. It was a precise material specification, choosing the right stone for the right job based on its properties and the symbolic importance of the space it would define. The location also solved the single greatest logistical puzzle: the movement of those imported stones. The plateau's northern edge rises just a few hundred meters from what was, in ancient times, a branch of the Nile. By extending canals to create a harbor at the very base of the site, they transformed the river into a direct delivery system. Heavy granite could travel by water for 500 miles, then be offloaded almost directly onto the construction grounds. This strategic placement minimized the most difficult leg of the journey, the overland haul. Every aspect of the site selection, the bedrock, the local quarry, the river access, was a calculated decision that reduced labor, increased efficiency, and leveraged the natural world as a construction partner. The pyramid did not conquer the landscape. It grew from it, a collaboration between human ambition and the enduring bones of the earth. That profound dialogue with the landscape was guided by a purpose far greater than mere construction. Every precise angle, every seamless joint was not an end in itself. It was a means to a sacred end. In the ancient Egyptian worldview, the pyramid was far more than a tomb. It was a resurrection machine, a celestial designed to propel the pharaoh's soul from the earthly realm to the eternal stars. This was not a poetic metaphor, but a core religious belief that shaped every single engineering decision. The structure had to be perfect because a flawed pyramid was a broken vehicle, a spiritual ship that could not complete its cosmic voyage. Imagine the stakes. This was not a matter of aesthetic preference or architectural pride. The entire purpose of the monument, the very reason for its existence, and the immense national effort behind it, hinged on its flawless execution. A crooked passageway might misdirect the pharaoh's spirit. An unstable chamber could collapse and trap his essence forever. A misaligned northern shaft might fail to point his soul toward the imperishable stars of the circumpolar region. This symbolic imperative created a cultural mandate for perfection unlike any other. It transformed the engineering challenge from a technical problem into a sacred duty. The precision we marvel at today was not an optional extra. It was the non-negotiable requirement for the monument to function. This fusion of the spiritual and the practical is the key to understanding their relentless drive for innovation. The need to build a perfect ramp to the heavens is what forced them to master celestial alignment with such breathtaking accuracy. The requirement for an eternally stable vessel for the king's spirit is what pushed them to understand load distribution, to invent corbelled ceilings like in the Grand Gallery, and to select stones of specific symbolic strength. The practical method of the ratio that defined the slope was not just a building code. It was a sacred geometry, a mathematical formula that encoded the very rays of the sun god Ra, along which the pharaoh would ascend. Every worker, from the quarryman to the surveyor, was not just a laborer. He was a priest of precision, contributing a vital part to a functioning divine mechanism. This is why the lost method feels so complete, so holistic. It was never just about moving stone. It was about orchestrating matter to serve a transcendent purpose. The technology was inseparable from the theology. The crane and the chant, the lever and the prayer, were two sides of the same coin. This cultural engine, this unwavering belief that their work had cosmic consequences, is what fueled the 20-year marathon of meticulous execution. It provided the ultimate motivation, the profound patience, and the unyielding standard that turned a mountain of stone into a perfect, silent machine, waiting for a moment of spiritual ignition that we, from our modern perspective, can only begin to imagine. This profound spiritual imperative demanded a toolkit of equal precision. Yet when we examine the actual tools left behind, a fascinating paradox emerges. The ancient Egyptians built a monument of staggering complexity, using what appears, at first glance, to be a shockingly simple collection of implements. Their primary metal was copper, a relatively soft material compared to the granite they were shaping. Their saws were without teeth, their drills without hardened steel bits. This was not a limitation, but a choice that reveals the core of their engineering philosophy. They understood that raw material strength was not the only path to mastery. Instead, they pioneered a smarter approach, one where intelligence and process amplified the power of simple tools. Their basic kit consisted of copper chisels and saws for softer limestone, heavy stone balls made of dolerite for pounding and shaping, wooden mallets and wedges, and meticulously knotted measuring cords. None of these items in isolation seems capable of crafting a pyramid. The magic was in their sequenced, intelligent application. Take the challenge of drilling a perfectly round hole through a slab of Aswan granite, a stone so hard it can spark when struck with steel. A modern power drill with a diamond tip bit would zip through it. They had no such technology, so how did they do it? Evidence on unfinished artifacts points to a brilliantly simple method. They would use a hollow tube, likely made of copper, attached to a wooden crossbar. Instead of relying on the copper to cut the granite directly, which would be futile, they used the tube as a guide for a far more effective cutting agent, abrasive sand. Workers would pour a slurry of wet sand, often containing hard quartz or corundum particles, into the groove. Then, as two people turned the drill back and forth with the crossbar, the copper tube would press the abrasive granules against the granite. Each rotation ground away a microscopic layer of stone. It was a process of relentless, patient abrasion, not sudden cutting. Over hours or days, the abrasive sand did the real work, slowly wearing a perfect, cylindrical core out of the granite. The copper tube simply contained the process and defined the shape. This is a profound lesson in resourcefulness. It demonstrates a mindset that saw tools not as singular solutions, but as components in a larger system. The real tool was the process itself, the understanding that hardness could be overcome not by a harder material, but by a smarter technique employing friction and patience. This principle applied everywhere. To shape a massive granite block into a smooth, flat surface, they did not have giant milling machines. They used those dolerite pounders, swinging them in rhythmic unison to crush the high points, constantly checking for flatness with simple wooden straightedges and slurry-filled leveling frames. The sound of the plateau must have been a constant, rhythmic percussion, the patient music of stone being persuaded into geometric perfection by stone. This focus on process over power allowed them to achieve tolerances that seemed to defy their era. It was a different kind of strength, one built not on force, but on the cumulative effect of countless small, correct actions. Guided by an unwavering standard and a deep understanding of how materials behave under persistent, intelligent effort. That patient percussion of stone shaping required a different kind of rhythm to sustain it, the daily, unwavering beat of mealtime for an army. The true scale of the Great Pyramid project is measured not just in cubic meters of stone, but in the millions of loaves of bread needed to fuel the hands that moved them. A rotating workforce of 20,000 to 30,000 people did not just appear at the site. They had to be housed, managed, and most critically, fed every single day for over 2 decades. This was a logistical challenge that rivaled the engineering of the monument itself, a silent, sprawling operation that transformed the entire Egyptian economy into a support system for a single, soaring goal. Archaeological excavations at the workers' village at Giza have peeled back the desert to reveal this hidden world. They uncovered not just barracks, but entire industrial complexes dedicated to sustenance. Massive bakeries with rows of clay ovens produced a coarse, nutritious bread that was the caloric backbone of the ancient diet. Adjacent breweries turned grain into beer, a thick, porridge-like drink that was a vital source of hydration, nutrition, and even a form of wage. The evidence is etched in the very trash of the site, enormous middens filled with the bones of cattle, sheep, and goats, and the remains of fish from the Nile, indicating a regular supply of protein. This was not a subsistence diet. This was state-provided provisioning on an industrial scale. Think of the supply chain this required. Vast estates across the Nile Delta and up the river valley, owned by the crown and temples, were dedicated to producing surplus grain and raising livestock specifically for the pyramid project. This agricultural output had to be harvested, processed, transported by boat along the Nile, and then distributed with meticulous fairness to the different crews at Giza. A scribe with a papyrus ledger was as crucial to the project as a mason with a copper chisel. He tracked every sack of grain, every jar of oil, every delivery of fish, ensuring that the human machine at the heart of the operation never faltered from hunger. This ability to mobilize and manage an entire nation's agricultural surplus for a single, long-term project is a staggering feat of ancient socioeconomic organization. It reveals a centralized authority with incredible reach and administrative precision. The pyramid did not just rise from the plateau. It rose from a foundation of bread and beer, a testament to the fact that the greatest constructions are always, ultimately, built by well-supported communities. The silent stones we admire today were lifted by people who were fed, housed, and part of a purposeful national endeavor, turning individual labor into a collective force that could literally move mountains. The rhythmic sound of stone shaping stone was not the only music within the pyramid. Step inside the king's chamber today, and you may notice something strange about the silence. It feels heavy, yet somehow alive. If you were to speak or clap your hands, the sound does not echo and fade as you might expect. Instead, it resonates, hanging in the air with a sustained, almost metallic ring. This is not an accident of construction. The entire chamber, built from massive hard granite blocks, is a giant, tuned resonating box. Some researchers believe this acoustic property is a profound clue, pointing toward a layer of the builder's knowledge we have barely begun to consider. Could they have harnessed sound itself as a tool? The idea sounds like the fringe of fantasy, but at its core, it is an exploration of vibration, a physical force as real as gravity. The theory suggests that by finding the precise resonant frequency of a massive stone block, the specific pitch at which it naturally vibrates most freely, and then exposing it to that frequency through chanting, drumming, or even specially tuned instruments, the builders could have temporarily reduced the friction between it and the ground. In essence, they might have made the stone float on a cushion of its own vibration, turning an impossible drag into a manageable slide. This concept, known as acoustic levitation, is not pure magic. Modern experiments with high-frequency sound waves have demonstrated the ability to suspend small objects in midair. The leap to multi-ton blocks is monumental, but the principle of using resonant energy to overcome gravitational and frictional forces is a legitimate area of physics. Even if full levitation was beyond their reach, the controlled use of sound could have had more practical applications. Think of a team positioning a final, multi-ton ceiling beam. Striking a block with a hammer produces a specific tone. A clear, pure ring indicates a solid, flawless piece of stone. A dull thud or a cracked sound reveals an internal flaw, a weak point that could fail under pressure. By listening to the stones, the master masons could have performed a kind of sonic quality control, ensuring only the most perfect materials were used in the most critical places. This transforms the construction site from a scene of silent toil into one of orchestrated vibration, where the hum of tuned chords and the rhythmic strike of mallets were not just noise, but diagnostic tools and potential aids. While these acoustic theories remain highly speculative and far from the mainstream consensus of Egyptology, they serve a vital purpose. They challenge us to expand our perception of what ancient engineering encompassed. It pushes us to ask if the builders possessed an empirical, hands-on understanding of wave physics that we, with our digital sensors and equations, are only now formally rediscovering. Their world was not silent. It was filled with the natural frequencies of wind, water, and stone. Perhaps their lost method included not just the science of sight and lever, but the science of sound, learning to listen to the very song of the materials they sought to command. The Great Pyramid stands as a silent witness to a golden age that could not last. Its construction was the pinnacle of an entire civilization operating at the peak of its unity and capability, a perfect alignment of will, wealth, and weather. But that alignment was fragile. The very system that built the pyramid was dependent on a stable, flourishing Egypt, and within centuries of its completion, that stability began to unravel. The end of the Old Kingdom was not a sudden, violent collapse, but a slow unraveling brought on by environmental and political strain. Decades of diminished Nile floods, likely linked to a changing climate, led to poor harvests and widespread hardship. The central authority of the pharaoh, which had commanded the nation's resources for the pyramid projects, weakened as local governors grew more powerful. The immense, state-directed economy that could feed 30,000 workers for 20 years gradually fragmented. The grand project of national unity gave way to regional concerns and survival. In this new reality, there was no place for another pyramid of that scale. The political will had evaporated, and the concentrated wealth needed to fund it was scattered. The golden age of colossal construction was over. This shift had a direct and profound effect on the engineering knowledge itself. The sophisticated method was not a secret written in a single scroll, locked away in a vault. It was a living tradition, a body of practical wisdom carried in the minds and hands of master builders, foremen, and skilled artisans. It thrived on continuous, large-scale practice. Think of it as a flame that needs constant fuel. The megaprojects of the Fourth Dynasty were that fuel. They provided the ongoing challenge, the daily problem-solving, and the structured apprenticeship system that kept the knowledge sharp, evolving, and passed down. When the project stopped, the flame began to flicker. The specialized guilds of stonemasons, quarry engineers, and no longer had a monumental workshop. The intricate rolls, the person who knew exactly how to calculate for a 51-degree slope, or the crew that mastered the harmonic lift of a 70-ton granite beam, were no longer in constant demand. Over generations, as smaller tombs and temples became the norm, the need for that specific, extreme precision faded. The knowledge did not vanish in a single day. It atrophied bit by bit over centuries. Processes were adapted for smaller works, and the deepest layers of the method, those refined through trial and error across multiple giant pyramids, simply faded from memory. They became stories, then legends, because the specific conditions that created them, a unified state, a booming economy, and a climate that could support a vast, non-farming workforce, never fully converged again in quite the same way. Later pharaohs of the Middle and New Kingdoms were certainly ambitious, building enormous temples, towering obelisks, and vast underground tombs in the Valley of the Kings. But these were different kinds of projects, with different engineering challenges. They required genius, but it was a genius applied to new problems, carving into bedrock, raising slender stone needles, or creating expansive columned halls. The specific, integrated system for building a perfect geometric mountain of stone was no longer directly relevant. The knowledge was not so much lost as it was retired, made obsolete by changing priorities and a changed world. The method became a ghost in the historical record, its echo felt only in the impossible perfection of the stones themselves. This is perhaps the most human aspect of the entire mystery. Great leaps of collective knowledge are often tied to their moment. They arise from a unique convergence of need, resources, and cultural focus. When that moment passes, the knowledge doesn't always travel forward intact. It recedes, leaving behind only the monumental proof that it once existed, a timeless question posed in limestone and granite, waiting for us to listen closely enough to hear its faded instructions. The stones may be silent, but they are not inscrutable. A new kind of archaeology is now listening to them, using particles from deep space to see through millions of tons of rock. This is Muon radiography, a technique that harnesses cosmic, rays to create an X-ray image of the pyramid's interior without ever touching a stone. Muons are subatomic particles that rain down from the upper atmosphere, passing effortlessly through solid matter. By placing sensitive detectors inside known chambers, scientists can map where these particles are absorbed by dense stone and where they pass through empty space. In 2017, the Scan Pyramids project announced a stunning find, a massive void at least 30 meters long located directly above the Grand Gallery. This is not a small crack or a natural fissure. Its scale and alignment suggest a deliberate architectural space, a hidden chamber, or perhaps a structural relief gallery designed to redistribute the incredible weight bearing down on the Grand Gallery below. Its discovery is a monumental reminder that we do not yet know the full internal blueprint of this ancient machine. Another non-invasive tool, infrared thermography, adds a different layer of perception. By taking precise thermal images of the pyramid's faces at sunrise, when the sun's warmth begins to soak into the eastern side, cameras can detect subtle differences in how quickly certain stones heat up. A block that warms faster than its neighbors likely has a different density or sits in front of an empty space, acting as a thermal insulator. These thermal anomalies, appearing as distinct cool spots or warm spots in precise geometric patterns, are like fever maps of the structure's health. They hint at variations in construction, potential gaps behind casing stones, or even the outlines of internal features long since buried. Each scan, whether from cosmic rays or heat signatures, provides a new data point in a growing digital model. This is how we are beginning to reverse engineer the lost method. We are not searching for a single papyrus manual. We are compiling a virtual blueprint, one invisible layer at a time, looking for the fingerprints of the builder's decisions in the very fabric of the monument. A thermal anomaly might trace the ghost of a long-removed internal ramp. A Muon map could reveal a network of counterweight channels. Every new void or density change is a potential clue, a silent answer to questions we are only now learning how to ask. The pyramid, it seems, is still communicating. It is telling us that its final secrets are not buried in the sand, but suspended within its own majestic geometry, waiting for our technology to finally catch up to its ancient, silent intelligence. That silent intelligence has echoed far beyond the desert sands, shaping our imagination for centuries. The unresolved question of how the Great Pyramid was built has become more than an archaeological puzzle. It is a cultural force in its own right. This single monument stands at the crossroads of history and mystery, a blank canvas upon which every generation projects its own beliefs, fears, and hopes about human potential. On one side, it has inspired rigorous scientific inquiry, pushing the boundaries of archaeology, engineering, and physics as teams from around the globe bring new technologies to bear on its secrets. On the other, it has fueled an entire universe of alternative theories, from ancient advanced civilizations to visitors from other worlds. This stark divide reveals something fundamental about us. The pyramid's perfection challenges our modern narrative of linear progress, the idea that we are always moving forward, that our technology is the pinnacle. Its existence whispers a provocative question: what if knowledge is not a straight line but a cycle? What if a culture can achieve a profound, specific sophistication, and then that understanding can fade, leaving behind only monuments that later ages struggle to explain? The story of a lost method resonates because it touches a deep-seated wonder about forgotten wisdom. It suggests that technological brilliance is not defined solely by electricity or silicon chips, but can be expressed through an intimate mastery of levers, water, sound, and social organization. This is not a call to mysticism, but a reminder. It asks us to broaden our definition of what it means to be advanced. A civilization that could coordinate thousands of people for decades, feed them all, and align a mountain of stone to the stars with handmade tools, was operating at a level of systemic intelligence that any modern project manager would recognize. Their tools were different, but their problem-solving was profoundly sophisticated. The enduring allure of the pyramid, then, is a mirror. We are fascinated by the gap between its physical reality and our understanding because, in that gap, we see the limits of our own assumptions. It forces us to confront the possibility that our ancestors were not primitive, but differently brilliant, and that some forms of their brilliance may be irrecoverable, not because they were magical, but because the specific cultural and environmental conditions that forged them are gone. In seeking their method, we are ultimately seeking to reconnect with a different way of seeing the world, one where human ambition worked in concert with nature's laws to achieve the seemingly eternal. The pyramid's greatest lesson may be humility, the quiet understanding that progress has many faces, and that some of the most impressive are carved not in circuits, but in stone, waiting patiently for us to learn their language anew. This drive to shape the earth with stone is a story written across the globe. From the misty highlands of Peru to the remote shores of a Pacific island, ancient cultures faced the same fundamental challenge: how to command the immense weight and stubbornness of rock. The Great Pyramid of Giza is the most famous chapter, but it is far from the only one. By placing it alongside other monumental achievements, we can see more clearly what made the Egyptian approach so distinct. Consider the at Baalbek in modern-day Lebanon. Here, 3 limestone blocks, each weighing an estimated 800 tons, form a foundation wall. That is over 3 times the weight of the largest stones in the Great Pyramid. The mystery of their transport from a quarry nearly a mile away and up a significant incline is profound. Yet the solution here seems to have relied on a different kind of ingenuity, one of immense leverage and perhaps a vast workforce on a singular, heroic lift, rather than the sustained, integrated production line of Giza. The stones are breathtaking, but the method appears as a monumental feat of momentary power, not a 20-year symphony of coordinated processes. Then look to the opposite side of the world, to the Inca walls of Peru. The precision here is almost unnerving. Enormous, irregularly shaped blocks of andesite are fitted together so tightly that not even a blade of grass can slip between them. This technique, known as ashlar masonry, achieved a result that rivals the Great Pyramid's casing stones for snugness of fit, but the Inca method was sculptural. They likely shaped each stone in place, patiently grinding one block against its neighbor, a process of custom fitting that created an interlocking, earthquake-resistant puzzle. It is a masterpiece of tactile adaptation, stone by unique stone. In contrast, the Egyptian method relied on standardization, on pre-shaping blocks to a common angle using the ratio so they would assemble into a predetermined, smooth plane. One approach celebrates the unique identity of each stone, the other the perfection of the repeatable unit. Finally, cast your gaze to the lonely expanse of Easter Island. Those haunting giant heads were carved from volcanic tuff and then transported, some weighing over 80 tons, across miles of rugged terrain to their ceremonial platforms. The leading theory suggests a rocking, walking method, where teams used ropes to sway the statues forward in a controlled, laborious shuffle. This is logistics stripped to its absolute essentials, a testament to sheer human determination and clever physics on a small, isolated island. Each of these sites, Baalbek, Easter Island, represents a brilliant, localized answer to the universal problem of megaliths. They show the incredible diversity of human ingenuity when confronted with stone. What sets the Egyptian achievement apart is not necessarily the individual techniques, many of which have parallels elsewhere, but the breathtaking scale of their integration. The Great Pyramid project combined celestial surveying, state-managed quarrying, a continental-scale transport network, a temporary but evolving internal infrastructure, a standardized mathematical blueprint, and a vast, sustained social organization, all operating in flawless concert for generations. While other cultures performed miracles with stone, the Egyptians built a civilization around the act of building. The evidence they left behind is not just the silent, perfect mountain. It is the quarries with their wedge slots, the worker villages with their bakeries, the diary of Murrah, and the celestial alignment frozen in the structure's orientation. This completeness of the archaeological record gives us a rare window into the system itself, not just its stunning final product. It allows us to trace not just the what, but the how, revealing a lost method that was less a secret and more a way of seeing and shaping the entire world. The pyramid's true foundation was not just stone, but grain. This immense 20-year endeavor functioned as the beating economic heart of the Old Kingdom, a grand engine of productivity that transformed the entire nation. Far from draining the state's resources, the project created a powerful cycle of employment and innovation. For a farmer whose fields lay fallow after the annual harvest, the pyramid site offered meaningful work and a reliable wage in bread, beer, and cloth. For a young man, it was an apprenticeship in a respected craft, a chance to learn masonry, surveying, or logistics. This was ancient stimulus spending on a colossal scale, a deliberate conversion of the Nile's agricultural bounty into a permanent, unifying symbol of national identity. The state collected taxes not merely as grain in a silo, but as labor and skill directed toward a common, transcendent goal. This economic model was a critical, living component of the lost method. It provided a stable outlet for human energy, distributed wealth across society, and prevented the idleness and potential unrest that could follow the harvest season. The project demanded, and therefore created, advanced administration. Scribes had to track thousands of workers, their rations, and their tools. Overseers had to manage complex schedules and supply chains. This bureaucratic machinery, forged in the heat of the pyramid's construction, became a lasting tool of governance, strengthening the state's ability to manage other projects, from irrigation canals to temple estates. In this light, the pyramid was never just a tomb for a single king. It was the ultimate civic project, a nation-building exercise of unimaginable scope. Its construction forged a shared identity, honed essential skills, and stabilized the economy by putting the nation's surplus to work in the most ambitious public works program in history. The monument we see today is not only a triumph of engineering, but the physical testament to an entire society working in concert, its economic vitality literally set in stone. That economic engine could only run if the people themselves believed in the journey. The most overlooked component of the Great Pyramid's construction was not made of stone or copper, but of shared conviction. This was a project that demanded more than skill. It required a profound psychological cohesion, a collective will strong enough to commit multiple generations to a single, staggering goal. The workers who hauled those blocks were not just building a tomb, they were participating in a sacred covenant that bound the fate of the nation to the cosmos. At the center of this belief stood the pharaoh, not merely a king, but a living god, the essential link between the people and the divine order of the universe, known as T. His successful ascension to the afterlife was not a private affair, it was a national security issue. If the pharaoh's spirit failed to join the eternal stars, the cosmic balance could be shattered, leading to chaos, poor harvests, and the unraveling of society itself. Therefore, every block laid, every perfect angle achieved, was an act of collective survival and spiritual insurance. The labor was a form of prayer in action, a direct contribution to maintaining harmony in this world and securing prosperity in the next. This shared ideology transformed backbreaking work into a sacred duty. It provided a why powerful enough to answer the how for 20 years. Imagine the difference between simply moving a rock and moving a rock that ensures your family, your community, and your entire civilization continues to thrive under the favor of the gods. That psychological framework is an intangible but utterly critical piece of the lost engineering method. It is the operating system that ran the entire project, turning the pharaoh's vision into a national mission. This deep-seated belief system also offered a powerful promise of reciprocity. While the pharaoh gained immortality, the people who made it possible were also granted a share in that eternal legacy. The honorific titles found in the workers' tombs near the plateau, names like Friend of Khufu, are deeply revealing. They were not slaves erased by history, they were commemorated participants. Their labor earned them status, a proper burial, and the belief that they too would benefit from the cosmic order they helped uphold. This created a powerful cycle of motivation, blending spiritual purpose with social recognition. The project manager's most brilliant tool may not have been a lever or a ramp, but a compelling story, one that gave every individual, from the quarryman to the scribe, a meaningful role in a narrative far larger than themselves. This ability to align thousands of minds and hearts toward a single, long-term objective is a staggering feat of social psychology. It speaks to a universal truth about human achievement. The greatest physical wonders are always, at their core, manifestations of a shared dream. The stones of the pyramid are heavy, but they are not as heavy as a lifetime of purposeless toil. The ancient method understood this profoundly. It channeled the immense weight of human effort by first giving that effort a transcendent meaning, lifting the spirit so that the body could lift the mountain. We can now assemble these pieces into a working model, a step-by-step sequence that transforms theory into a plausible 23-year timeline. This reconstruction is not a definitive blueprint, but a synthesis of the clues, showing how the lost method might have functioned as a single, elegant machine. The first 5 years were not about stacking stone, but about building the stage. Master surveyors, using the stars, would have established the perfect north-south axis on the Giza plateau, a line that would govern every measurement to come. While the site was being leveled, quarrying operations began simultaneously at and Aswan. The most critical and invisible work, however, was the creation of infrastructure. Engineers would have overseen the digging of canals from the Nile, extending a watery highway to the very edge of the construction site. At the same time, the initial ramp system, likely a broad, straight ramp for the lower courses, would have been built from desert rubble and packed earth, its foundation laid with the same care as the pyramid's own. These first years were an investment in process, creating the logistical channels that would make the next phase possible. From year 5 onward, the project shifted into its relentless, rhythmic cycle. This was the heartbeat of the operation, a continuous parallel process model of stunning efficiency. At the quarries, teams worked in shifts, splitting blocks with wooden wedges and rough-shaping them with stone pounders. These blocks were loaded onto barges and floated down the Nile and into the newly built canals, arriving at the Giza harbor. There, crews transferred them onto wooden sleds. Paths of wet sand turned a Herculean drag into a manageable pull, guiding the stones to the base of the growing ramp. As the pyramid rose, the ramp itself evolved, perhaps transitioning from a single straight incline to a more complex zigzag or internal spiral. Blocks were hauled upward, tier by tier. For the final, precise positioning, especially with the gigantic granite beams for the inner chambers, the counterweight systems within structures like the Grand Gallery may have been engaged. Using sand-filled containers to lift weights that human muscle alone could not. Crucially, this was not a linear process. While the outer core rose, specialized teams worked inside the growing mass, constructing the descending passage, the subterranean chamber, the ascending passage, and the Grand Gallery itself. They built the internal architecture from the inside out, even as the mountain closed in around them. This concurrent construction is a key to their speed, a symphony of coordinated labor where no team waited for another to finish. The final act, spanning the last 3 years, was one of breathtaking precision and dismantling. With the core structure complete and the summit stone, or capstone, placed, the focus turned to the exterior. The brilliant white limestone casing stones, carefully stockpiled and pre-shaped, were now brought into play. Workers likely applied these smooth, polished blocks from the top downward, using the very ramp they were now carefully deconstructing. As they worked their way down, they removed the earthen ramp behind them, revealing the flawless geometric form for the first time. This final phase was a beautiful reversal of the construction process, an unveiling. The temporary infrastructure, having served its purpose, vanished back into the desert, leaving no trace for later ages to find. What remained was the pure, perfect shape, a mountain of stone that had grown from the landscape and now seemed as eternal as the bedrock itself. This integrated model shows the method not as a collection of tricks, but as a holistic system. It was a masterful balance of long-term vision and daily iteration, of monumental ambition and patient, granular skill. The pyramid did not just get built, it unfolded according to a plan that understood time, physics, and human cooperation as materials to be shaped, just like the stone. A perfect plan could not survive contact with 2 million stones. The Giza Plateau was not a sterile blueprint come to life. It was a dynamic, dusty workshop, a laboratory operating at a scale we can scarcely comprehend. For 20 years, engineers and foremen faced a relentless stream of real-world problems. A foundational layer, meticulously leveled, might settle unevenly under its first colossal load. A granite beam, hauled with unimaginable effort into the Grand Gallery, could reveal a hidden internal flaw under stress. A ramp designed for the lower courses might become impossibly steep and unstable as the pyramid soared toward the sky. The true genius of their method was not in avoiding these issues, but in having a culture built to solve them in real time without halting the entire monumental machine. This was adaptive engineering on a live site, where every mistake was a lesson carved directly into the project itself. We see whispers of this problem-solving etched in stone, quite literally, inside the hidden relieving chambers above the king's chamber. Here, amid the immense, silent slabs, are casual markings left by the crew, what archaeologists call workmen's graffiti. These include simple directional notes like "this side up" and crew names such as the Friends of Khufu Gang, but they also include small, practical adjustments. Blocks might be numbered out of sequence, or a stone might show a chiseled correction to its intended placement. These are not errors, they are the fingerprints of intelligent adaptation. They tell us that the teams on site had the authority and the knowledge to make minor corrections as they went, to adjust the plan to the reality of the stone in front of them. This reveals a decentralized, responsive intelligence. The master architect provided the grand vision and the mathematical rules, the but the foremen and masons on each tier were trusted experts, empowered to diagnose a problem and implement a fix. If a block did not fit perfectly because of a slight bulge from quarrying, they did not send it back. They worked it in place, grinding it down until the joint was true. If a course began to drift out of alignment, they could adjust the angle of the next layer to compensate, steering the entire massive face back toward its perfect geometric destiny. This flexibility was a safety valve in the system. It meant the project was resilient. A single flaw did not doom the whole. The method was not a brittle, preordained script, but a living process, a conversation between the ideal plan and the physical reality of limestone and granite. It was engineering as a craft, requiring constant judgment, keen observation, and the confidence to innovate under the pressure of a pharaoh's eternal deadline. The pyramid, therefore, is not a monument to a flawless, unchanging idea. It is a monument to human ingenuity's ability to adapt, to learn from the material world, and to keep moving forward even when the path required a sudden, intelligent turn. The immense stone mountain at Giza was a peak the civilization never attempted to scale again. Yet the sophisticated engineering mind that conceived it did not vanish with the last casing stone. It simply evolved, its principles flowing like the Nile into new channels of expression. The age of the colossal pyramid passed, but the knowledge that built it became the bedrock for everything that followed. You can see this transformation etched across the landscape of Egypt for the next 2,000 years, not in the form of perfect triangles, but in the forest of columns at Karnak and the towering needles of stone at Luxor. These later monuments are the true legacy of the lost method, proof that the genius was not in a single blueprint, but in a flexible, enduring understanding of stone, scale, and human coordination. The great temple complexes demanded a different kind of wonder. Instead of external geometric perfection, the goal became internal awe, the creation of sacred spaces that humbled the human spirit. At Karnak, the hypostyle hall is a petrified forest. 134 columns, some 70 feet tall, and so thick it would take 5 people with arms outstretched to circle one, hold up a ceiling of massive stone slabs. Lifting these slabs, these architraves, to such a height presents a problem eerily similar to placing the granite beams in the king's chamber. The solution likely drew from the same well of ingenuity. Builders would have constructed great earthen ramps, packing sand and rubble against the already erected columns. Using the same system of sleds, ropes, and levers, and perhaps even refined versions of the counterweight principles hinted at in the Grand Gallery, they would have inched these multi-ton ceiling blocks into position. Once the roof was secure, the ramp material was hauled away, leaving the towering columns standing free, a feat that mirrors the final dismantling of the pyramid's own construction ramps. This was not a forgotten skill, but an adapted one. The mastery of moving immense weight vertically had been learned on the slopes of Giza and was now applied to create enclosed mountains of carved stone. The obelisk represents perhaps the most audacious evolution of this skill. A single piece of red granite, at Aswan just like the pyramid's inner stones, shaped into a slender, four-sided pillar tapering to at the top. The unfinished obelisk still lying in the Aswan quarry is a breathtaking lesson in scale. It would have been 137 feet long and weighed nearly 1,200 tons. Transporting and erecting such a fragile-looking monolith was the ultimate test of precision engineering. The process began, as always in the quarry, with workers painstakingly separating the stone from the bedrock, using the same familiar technique of channels and wooden wedges. For transport, the obelisk was likely dragged on a gigantic sledge to a specially built, extra-wide barge for its journey down the Nile. The The true miracle was the erection. Historians and engineers theorize a method that speaks to profound confidence. The barge would be maneuvered into a flooded trench next to a prepared pedestal. The obelisk, carefully pivoted, would have its base positioned against the pedestal's foundation. Then, as the trench was slowly drained, the barge would sink, lowering the obelisk's base into place. But it would still be lying down. To raise it, crews would have built a giant, funnel-shaped masonry structure around it, filled with sand. As they meticulously removed sand from the bottom of the funnel, the obelisk would have pivoted upward, grain by grain, in a perfectly controlled ascent until it stood vertical. This breathtaking procedure, a symphony of hydrology and granular physics, shows the pyramid builders' intellectual descendants thinking with the same elegant practicality. They were still using natural forces, water and sand, to do the heavy lifting, applying old principles to new, dazzling forms. Meanwhile, the stoneworking expertise honed in shaping millions of uniform blocks for smooth plains found a new outlet in incredible detail. The energy once focused on mathematical exactitude now poured into artistry. The same hands that could polish a casing stone to a mirror finish now carved the intricate hieroglyphs that cover every temple wall, column, and statue. The tools were familiar, copper chisels and abrasive sand, but the application was microscopic in its precision compared to the monumental scale of the pyramid. This shift from macro-engineering to micro-engraving reveals the full diffusion of the method. The cultural obsession with permanence and perfect execution never faded, it simply changed its canvas. The lost pyramid-building method, therefore, was never truly lost. It underwent a metamorphosis. The integrated system, the logistical networks, the lifting techniques, the material science, the skilled labor organization, did not disappear. It fragmented and specialized. The master builder became the temple architect, the quarry engineer became the obelisk specialist, the stone mason became the master sculptor. The knowledge lived on in guilds and workshops, passed down through generations, but it was applied to a diverse array of projects over centuries rather than concentrated on a single 20-year megaproject. The legacy of Giza is not a void where knowledge once stood. It is the soaring hypostyle hall, the piercing tip of an obelisk against the sky, and the endless, beautiful stories carved in stone. The method was not erased, it was disseminated, weaving itself so completely into the fabric of Egyptian civilization that its origin point, the first perfect mountain, became a solitary, silent ancestor to everything that came after. The most persistent stories surrounding the pyramid are not found in ancient texts, but in modern imagination. They speak of impossible machines, visitors from distant stars, or a forgotten superscience that could soften stone like clay. These are compelling narratives, but they share a fundamental flaw. They are built on a profound underestimation of the very people who left us this monument. When we examine the ground, the real story is far more powerful. There is not a single shard of evidence for alien technology, advanced machinery, or a magical concrete. What we find instead are copper chisels worn down from endless cutting. We find stone pounders, simple wooden sleds, and the grooves in the bedrock from where wedges split the rock. This is not the debris field of a lost super-civilization. It is the toolkit of a Neolithic and Bronze Age society, operating at the absolute zenith of its capabilities. The idea of a lost, magical method is seductive because it offers a simple answer to a complex achievement. It suggests a single secret, a button that could be pressed to make the impossible easy. But the truth revealed by archaeology is more demanding and ultimately more respectful. The so-called lost method was not a piece of technology that could be stolen or broken. It was a cultural achievement, a temporary peak in pre-industrial engineering, logistics, and sheer human will. It was the product of a unified state with a singular focus, harnessing the labor and skill of thousands not through coercion, but through a shared belief and a well-organized system of support. To suggest aliens or a vanished science built the pyramid does more than ignore the evidence. It robs the ancient Egyptians of their genius. It takes one of humanity's greatest demonstrations of collective intelligence and credits it to someone else. Consider the implications. If an advanced civilization with anti-gravity devices or stone-melting lasers had been here, why would they use those powers to painstakingly quarry, drag, and polish millions of individual blocks? Why would they leave behind the crude, human-scale tools and the worker villages with their bread ovens and fish bones? The evidence we have points to a human-scale project, with human-scale problems solved through human-scale ingenuity. The ramps were made of earth and rubble, not a mysterious energy field. The stones were lifted with levers and counterweights, not sonic levitation. The precision came from knotted cords, sighting rods, and a mathematical rule called the not from a handheld laser level. This reality does not diminish the wonder, it amplifies it. Building the pyramid with cranes and computers would be a significant engineering feat. Building it with copper, rope, and limestone, coordinated across decades by a civilization that had not yet invented the wheel, is a staggering testament to what humans can accomplish with organization, patience, and a deep understanding of their world. Acknowledging this human triumph makes the pyramid more impressive, not less. It moves the story from the realm of fantasy into the realm of inspiration. It shows us that our ancestors were not primitive people waiting for a savior from the stars. They were innovators, problem solvers, and master organizers. They looked at a barren plateau and saw a foundation. They looked at a river and saw a highway. They looked at the unchanging stars and saw a blueprint. Their method may feel lost to us because we struggle to conceive of such sustained effort and such elegant simplicity. But it was never magic. It was the product of minds not so different from our own, applied with a focus and unity of purpose that stands as their true and most humbling legacy. The real mystery is not how they did it with alien help, but how they did it with nothing but their own brilliance, and why we are so reluctant to believe they could. That legacy of human brilliance now faces challenges its builders could never have foreseen. Our modern desire to understand the pyramid, to peer into its hidden chambers and decode its silent language, comes with a profound responsibility. This is not merely an ancient site. It is the world's greatest engineering textbook written in stone, and every page is fragile. The very forces that seek to unlock its secrets, tourism, scientific exploration, and a changing global climate, also pose the greatest threats to its survival. For over a century, the traditional approach to archaeology was often invasive. To find a chamber, you drilled a hole. To understand a passage, you cleared it with dynamite. These methods, born of an earlier era's curiosity, sometimes caused irreversible harm, scarring the monument in the pursuit of knowledge. Today, the ethical imperative has shifted dramatically. Modern archaeology is guided by a principle of minimal intervention. The goal is no longer to extract secrets at any cost, but to listen to the structure without touching it, to learn while leaving no trace. This is why techniques like Muon radiography and infrared thermography are so revolutionary. They allow us to see through stone, to map hidden voids and internal stresses, all while the pyramid sits undisturbed under the desert sun. It is a conversation, not an interrogation. This careful balance defines our current quest. We are driven to uncover the lost engineering method, to solve one of history's great puzzles, but we must do so with the humility of a student, not the entitlement of an owner. Every scan, every drone survey, every environmental study is conducted with a single, overriding question: how can we learn without altering? The preservation challenge extends far beyond the research lab. The pyramid exists in a living environment. The breath of millions of visitors each year introduces humidity and salts into its internal chambers, potentially weakening the ancient stone from within. The vibrations from nearby urban development, and even the subtle, cumulative effects of a warming planet, pose long-term risks to its structural integrity. The brilliant white limestone casing that once gleamed across the desert is almost entirely gone, much of it repurposed for buildings in Cairo centuries ago. What remains of the outer shell is now exposed to the elements, to wind erosion and the chemical reactions of modern pollution. Our duty, therefore, is twofold. We must protect the physical monument from further decline, employing careful conservation to stabilize its structure and manage the impact of human presence. And we must protect the integrity of the unanswered questions it holds. Rushing to physically open every suspected void could cause collapse or damage we cannot repair. Sometimes the greatest respect for a mystery is to preserve it, to allow future generations, with technologies we cannot yet imagine, the chance to seek their own answers. This ethical framework transforms the search for the lost method from a technical puzzle into a moral one. It asks us to value the pyramid not only for what it can tell us about the past, but for its own sake, as a testament to human achievement that belongs to all of humanity and to the future. The stones have endured for 4.5. Our role is not to conquer their secrets, but to become their stewards, ensuring that this silent teacher remains standing, patiently waiting for the next curious mind to learn its language for centuries to come. This brings us to a deeper, almost philosophical puzzle. What does it truly mean to say an engineering method is lost? The physical principles the ancient Egyptians used are not a mystery to us. We understand leverage, we master hydraulics, we calculate geometry with computers far beyond their knotted cords. The core ideas of project management, of organizing thousands of people toward a single goal, are the backbone of our modern world. So nothing, in a pure scientific sense, has vanished. What has faded is something more subtle and profound, the specific cultural context that fused those principles into a single, breathtaking act of will. The method was not a list of instructions in a manual. It was a mindset, a way of seeing the world where every resource, from a star's path to a farmer's labor, was a thread in the same grand tapestry. Their society was organized around a unifying belief that gave this technical effort its transcendent purpose. We have the science, but we lack the symphony. Rediscovering their method, then, is not about finding a hidden scroll with diagrams of alien machines. It is an exercise in historical empathy. It is about reconstructing a state of mind, a collective consciousness that could look at a barren plateau and not see an obstacle but a canvas. It could look at a multi-ton block and not see an immovable object, but a single component in a geometric equation. It could mobilize a nation not through coercion, but through a shared story that wove individual effort into cosmic significance. This is what feels lost to us, the seamless integration of belief, bureaucracy, and brute physics. We excel at the individual parts. We build skyscrapers with cranes of steel, but could we coordinate their construction for 20 years using only copper, rope, and a sacred covenant with the stars? We manage global supply chains with digital networks, but could we feed and house 30,000 workers using only papyrus ledgers and a fleet of wooden barges? The challenge is one of holistic vision. Their method was an ecosystem of innovation. where solving a transport problem meant re-engineering the landscape with canals, and solving a lifting problem meant observing how water displaces weight in a bucket. Each solution was not isolated. It was a branch connected to the same deep root of practical understanding. To walk in their footsteps is to temporarily set aside our assumptions about what technology must look like. It asks us to consider engineering not as the application of power, but as the art of elegant persuasion, of convincing stone to rise and water to lift by understanding their inherent nature. So the blueprint we are piecing together is not for a pyramid. It is for a way of thinking, one that reminds us that our greatest structures are always built first in the imagination, forged by a culture's unique ability to dream as one. The blueprint we have been assembling points toward a single, powerful conclusion. The true lost method of the Great Pyramid was not a secret lever or a hidden ramp design. It was something far more profound, a fully integrated operating system for the impossible. Imagine the project not as a single challenge, but as a web of interconnected puzzles. The ancient engineers did not solve these puzzles in isolation. They built a network of solutions where each answer supported and enabled the next, creating a synergy more advanced than any single tool could ever be. This began with the sky and the stars, with celestial surveying that anchored the entire geometric vision to the cosmos. That precise alignment dictated the placement of every stone. But to place the stones, you first had to move them. This is where geological savvy met water-based logistics. They chose a site with a solid limestone foundation and a nearby river branch, then engineered that landscape, digging canals to turn the Nile into a direct delivery route. The quarrying technique, using expanding wooden wedges, was a clever application of physics to harvest the raw material. The transport method, using wet sand to reduce friction, was another. These were not random tricks. They were deliberate choices from a shared understanding of material properties. Then came the vertical ascent, the domain of ramp and lever mechanics. The temporary evolving ramp system provided the broad highway upward, while counterweight levers, perhaps scaled-up versions of the simple shadoof, allowed for the final, delicate positioning of multi-ton blocks. This mechanical lifting was synchronized with on-site finishing, the patient grinding of stone against stone that turned rough blocks into a seamless, polished plane. But none of this physical engineering would have lasted a single season without the human engine behind it. This is where unparalleled social organization completed the system. A state-managed economy redirected agricultural surplus into bread and beer, feeding a rotating workforce of skilled laborers. A hierarchical but motivated bureaucracy, documented by scribes like Muon, tracked every delivery and work hour. And a unifying cultural belief transformed labor from a chore into a sacred contribution to cosmic order. Each of these components, celestial, geological, logistical, mechanical, and social, was an engineered solution to a discrete problem, but the genius was in their integration. The canals solved transport, which enabled the steady supply of stone for the ramps. The ramps delivered blocks to the masons, who used their finishing techniques to achieve the precision demanded by the celestial survey. The social organization fed and motivated the workers who operated every part of this chain. A failure in any one link, the food supply, the water level in the canals, the accuracy of the ratio, would have stalled the entire monumental machine. This systems thinking is what feels so startlingly modern to us. They were not just builders, they were master orchestrators. They understood that to build a mountain, you must first redesign the world around it, turning the river, the desert, and the very society itself into components of the construction. The lost method, therefore, was this holistic mindset. It was the ability to see a 20-year, nation-spanning project as a single, solvable equation, where physics, logistics, and human spirit were variables that could be balanced. The pyramid is the proof that they solved it. It stands not as a collection of ancient techniques, but as the physical output of history's first and perhaps most complete integrated system. The Great Pyramid stands not as a mystery that belittles us, but as a challenge that inspires. Its silent stones do not whisper of secrets we can never know, but of a potential we have always possessed. The lost engineering method was not a magic spell, but a testament to what humanity can achieve with patient observation, seamless collaboration, and an unwavering sense of purpose. It shows us that the most profound innovation is often about perfecting the simple, not inventing the complex. They did not seek a new material or a supernatural force. They mastered the materials they had, listening to the song of the stone and the rhythm of the river, turning everyday physics into a language for the eternal. Their genius was in seeing the system, in understanding that a perfect angle in the sky required a perfect organization on the ground, that feeding a worker was as critical to the project as fitting a block. This holistic vision is their true legacy, a blueprint for thinking that transcends any single tool or technique. As we continue to probe its secrets with respect and advancing science, we do more than solve an ancient logistical puzzle. We reconnect with a pinnacle of human potential, a moment when an entire civilization aligned its will toward a single, staggering expression of belief and capability. It reminds us that our own greatest monuments, whether of glass, steel, or social progress, are built on that same foundation: observation, collaboration, and purpose. The pyramid's final lesson is one of quiet confidence. It asks us to look at the impossible tasks of our own age not with despair, but with the knowledge that the tools for monumental change are often already in our hands, waiting for the vision to assemble them into something timeless. What other forgotten wisdom might our ancestors hold, etched not in papyrus, but in the very landscapes they shaped? Share your thoughts in the comments below, and subscribe to journey deeper into the enduring mysteries of our shared past.